Hello everyone, let's start in section 12.2, arithmetic sequences and series. Now previous to this, in the previous lecture, we talked about in general sequences and series. In section 12.2, we're looking at a specific category or group of sequences and series, namely the arithmetic sequences. Now what makes a sequence arithmetic is that there is a fixed difference between successive terms. So for example, let's say I have a series that's made up of 8, 11, 14, 17, and so on. So you can kind of see from this that I have a fixed difference between successive terms, in this case 3. So if I go 11 minus 8, I get 3. 14 minus 11, 3, and 17 minus 14. All those differences are fixed. And for the purpose of what we do here, for our differences, you look at the second term minus the first term, and that's going to be a difference. We call that constant D for fixed difference. Okay, it makes a difference if you do A1 minus A2, doesn't it? In my example, if you do a sub 1 minus a sub 2, the difference would be negative 3, which is incorrect. So you always go next term minus the one before. So the second term is when you get the first term, you add the common difference to it. How do I get to the third? Well, you add 3 to the second term. The fourth, you add 3 to the one before. So we can, like this, we can define the sequence recursively as, to get to the next term, you add 3 to the previous term, and minus 1 is the previous term. And there you have it. This is a recursive definition of an arithmetic sequence. A recursive definition. Okay, and this recursive definition, remember, the first term is just whatever, call it A, whatever the first term might be. So in general, we can say that A sub n is A sub n minus 1. I had plus 3. I can say now A sub n is A sub n minus 1 plus that constant or fixed difference as you go from one term to another term. And there you have it. We have the recursive definition. All right, and I'm going to let again A1 be A for this one. Now we are interested also in the functional form of a sequence. So remember, in other words, we want to know what is f of n, right? What is the functional form, not the recursion, because recursion doesn't give me the formula for it, if you will. It gives you an expression for the next term in terms of previous term or terms. Okay, so how are we going to find f of n? Well, we were told the first term is a, right? The second term is going to be a1, a sub 1 plus a common difference. To get to the third one, you add the previous one, you add d to the previous one. Now, a sub 2 itself, remember, it was a sub 1 plus d. That's from this step before, plus a d, so I get a sub 1 plus 2d. If I want to know a sub 4, I can do d plus previous term, but then this is the previous term to a sub 4. It's going to be a sub 1 plus 2d plus another d. And this way I'm kind of creating, not kind of, but I am creating a pattern that only utilizes a first term, a sub 1, and a common difference. So if I continue on with this pattern, what we see here, if the index is 4, the coefficient on d is 1 less. So for a sub n, therefore, it's going to be first term plus n minus 1 times common difference. And this is the functional form. Remember, a sub n is indeed the same as f of n. So that is the functional form of an arithmetic sequence where n is a natural number. N is natural. Okay, remember, natural numbers are your counting numbers. And we can now write the terms of this sequence as first term, first one plus a common difference, first one plus twice the common difference, and so on, all the way up to the nth term, which is directly above what I'm writing, and so on. Okay. Now, how do we know a sequence is arithmetic? Remember, it's important to have a constant fixed difference. So in my example, let's say we want to show that a sequence that is given by, let's say, 2n minus 5. I want to show that the sequence is arithmetic. To show this is arithmetic. Okay. Well, to do this, I need to show that the difference between nth term, a sub n, remember, is 2n minus 5. What does a sub n minus 1 look like? That's when you change your n to n minus 1. That's a sub n minus 1 minus 5. Now let's do a sub n minus a sub n minus 1. These are two successive terms, right? Two back-to-back terms. So if the difference in general is constant, then we've shown this sequence is indeed arithmetic. All right, so I'm going to do 2n minus 5 minus 2 times n minus 1 minus 5. And that's what a sub n minus 1 is, right? From the previous step. And then we can do the simple algebra. 2n minus 5 distribute. Negative 2 times n is negative 2n. Negative 2 times negative 1. Or inside, I get negative 2 minus 5, negative 7. Negative on the outside is positive 7. Correct? Plus 7. Then I can add opposites. 7 minus 5 is 2. Which is a constant. So any number would work as long as it's a constant difference. And that's what indeed the common difference D is. So if I was to write the first few terms a sub 1, a sub 1 is going to be 2 times 1, right, minus 5 equal negative 3. I'm using the formula which defines it. What is a sub 2? Well, a sub 2 is when you add the common difference to the previous term. It's going to be negative 3 plus 2, which is equal to negative 1. Right? I'm doing it recursively. Or you can plug it in this way. A sub 2 is 2 times 2 minus 5, using the formula. Using that formula. Either way it works. Remember? Either recursively or using the function. Once we have the first term common difference, usually we use the recursion. It's easier. So first term, negative 3. Second term, we add 2. Add 2 to negative 1, you get 1. Add 2 to 1, you get 3. Add 2 to 3. You see how fast you can generate them now without each time going back, plug it in, and simplifying it. And there you have it. That's what the sequence looks like. Okay, let's do another example here. Suppose I want to find now the nth term. Let's say I'm going to give you the first term and the common difference. So the first term is 8, and the common difference, let's make it negative 7. Suppose we have that, and I want to find a sub n. Okay, and let's just do something wacky. Let's find the 80th term in the sequence also. So in order to find the a sub n, we have a formula. And remember, this is, by the way, only for arithmetic sequences. The formula that we mentioned, this one, a1 plus n minus 1d. Only for arithmetic this works. It doesn't work for other sequences. So please be mindful of that. A sub n is going to be first term plus n minus 1. Common difference is negative 7. And if I simplify this, I get 8 minus 7n plus 7, or 15 minus 7n. And there you go. That's the general term. That's why n's going to be in there. That's what's called general. It can give you any term for any natural number n. So let's say I want to know what it is for the 80th term. The 80th term, so a sub 80, you put 80 for n. 7 times 80. And that's going to be whatever. 7 times 80, 15 minus 560. And that's going to be negative 545. See how that works? I can find any term. I can find the 50th term, the 5,000th term, doesn't matter. Okay. Let's do another example. For this example, this time I'm going to make up a sequence: 2 5/2, 3 7/2, and so on. And let's say this is an arithmetic sequence. I want to find, let's do what we did above, find a sub 80. What does the 80th term look like? Well, you don't want to count all the way to 80th term, right? Until you get there, because there's room for error and it's really tedious. We don't want to do it. That's not the right way to do it. What if I want to find a sub 8,000? Am I going to count to 8,000th term? Most likely not. So let's find the first term, which is clearly obvious. It's the first one in the sequence. And I do need a common difference. The common difference, any two back-to-back terms would do. So I can do 5/2 minus 2. The difference is going to be 5/2 minus 4/2 is 1/2. There you go. Or if you want, you can do 3 minus 5/2. That's a half. Or you can do 7/2 minus 3. That's a half. I usually do the first two. That just gets me there just as good. So we do have the common difference and we have the first term. So we are golden. To find the 80th term, again, we go to the formula we had. It's going to be first term plus parentheses n minus 1 times the common difference using the formula that we have up here. Okay, same formula. And if I do that, what am I going to get? Well, 80 minus 1 is 79. That's 79/2. 2 plus 79/2. 2 mean 4/2, so that makes it 83/2. And there we have it. That would be the 80th term. Now that's about as far as we want to know about or learn about arithmetic sequences. Let's talk about their arithmetic series now. Okay. So let's talk about the nth partial sum. This time, we don't want to just list the sequence. We want to find the sum of the terms. So for instance, the one we just did, what is the sum of 2 plus 5/2 plus 3 plus 7/2 plus ... plus 83/2, the 80th term. So this is S sub 80 in our notation. We want to find the formula for the nth partial sum of an arithmetic series, not other kind of series, arithmetic. So how are we going to do this? Well, to do this, let's see if we can derive the formula for it. The nth partial sum is a1 plus a2 plus a3 plus ... plus a sub n, right? Now, I can write each term in terms of the, let's say, first term and a common difference. So a2 would be a1 plus d. a3 would be a1 plus 2d, right? And so on, plus an would be a1 plus n minus 1 times d. So I have written every term in terms of the first term and the common difference. True? Now, if you look at the terms in here of that what I have written here, if you look at the first terms, all first terms have a sub 1 in them. So I'm going to go a sub 1 plus a sub 1 plus a sub 1 plus ... plus a sub 1. That picks up this one, this one, this one, ... this one. You see that? So I'm looking at only the first terms in here. Now, how many a sub 1s do I have? Well, there are n terms, right, in this series. So I'm going to have n terms. In other words, I have n a sub 1s. So I can just that part I can write as n a sub 1s, correct? Now let's look at the common differences here. The common differences start with 1d, 2d, and then next one will be 3, 4, 5, all the way to n minus 1 times d, correct? So I can go ahead and actually write that one also. I can write it as d plus 2d plus 3d plus dot 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 plus n minus 1 d. That's how many d's are in that list. Now, I can factor a d, couldn't I? If I factor a d from the bracket, I get d times 1 plus 2 plus 3 plus dot 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 plus n minus 1. And in our previous lecture, section 12.1, we had a formula. Let me recall what the formula was. That the sum of k from 1 to n, you multiply the upper limit times upper limit plus 1 divided by 2. Remember, this comes back from previous section. Let me real quick show you that. And that was this right in here. See this one? So we've seen that in the previous section. Again, the way this formula works is whatever the upper limit, you put it here, and then you add one more to the upper limit to get the next term. Well, I have 1 plus 2 plus 3 plus n minus 1. So this is my upper limit. Now I can write this as n a sub 1 plus d times n minus 1. That's this part. And times 1 plus that. That's n minus 1 plus 1 divided by 2 using the formula from previous section. And remember, in the previous section, the upper limit was n. Now it's n minus 1. So we have to make adjustment for that. And then what do we get next? Well, 1 minus 1, that's 0. So the fraction is just n minus 1 over 2, correct? And I can write it like this. I can go n a sub 1 plus n over, I'm going to bring the n, this n outside, out to the front, n times d by n minus 1 over 2. That's just another way to write that expression. Okay, and now I can factor the n from both of these. In fact, let's factor n halves, n divided by 2. Now the first term doesn't have a 2. I can write it as 2 over 2, so I can factor a half. Therefore, n is factored out. From the first term, all that remains is 2a sub 1. And from the second fraction, because n halves is taken out, I have n minus 1 times common difference d. And there you have it. We have a formula, which is usually this is what's published in the textbooks. The formula for the nth partial sum is going to be n over 2, 2a sub 1 plus n minus 1 times the common difference. And this is the formula for the nth partial sum of an arithmetic sequence. I'm sorry, arithmetic series. A sequence is just the terms separated by comma. A series is when we add them. Now, this one, we can also manipulate this a little bit within the brackets. Look at the within brackets. I have 2a1, so I can write it as a1 plus another a1, right? Isn't that 2a1? Right, I have 2a1 plus n minus 1d. Now, this part a sub 1 plus n minus 1d, isn't that the nth term of an arithmetic sequence or series? Either way. So what I'm doing is so this is a sub 1 plus a sub n. Therefore, the nth partial sum can also sometimes be written as a sub 1 plus a sub n. There are two versions of this formula, in other words. So when do I use which one? If you know the first, and if you know the nth term, use this formula. So for example, suppose I have 1 all the way up to 1,000. That's my first term. That's my 1,000th term. So I'm looking at the first 1,000 counting numbers, and I want to know what is the sum of the first 1,000 counting numbers. Well, that's 1,000 divided by 2. I just add first term plus last term, and that would be the sum, right? Which is 500 times 1,001, which is 500,500. That fast. There you go. So if you know the first and last term, and you can do this. But if I don't know it, then you can use the one above. All right, if you don't know the first and the last terms, you can use the one above. Now, let's take a look at some example of doing this, and we'll be done. Let's say I want to find a sum for this first example. In fact, all of these, we're going to find the sums. So I want to find the sum here of even numbers, 2, 4, 6, all the way up to 70, plus 70. Now there are 35 numbers there, right? There is a common difference of 2, by the way, here, right? 2, so the difference is 4 minus 2 is 2. First term is 2. Now, I want to know what is the sum of, there are, again, how many terms in here? 35 terms. Sum of the first 35 terms. I can use the formula n over 2, a sub 1 plus a sub n, because I know the first one, I know the last term. And that's going to be 35 divided by 2 times 2 plus 70 makes 72. That's 35 times 36. 72 halves is 36. And the product's going to be 1,260. There you go. That will be the answer. Now, I could have done this another way. 2 plus 4 plus 6 plus ... plus 70. I could have factored the 2. If I factor the 2, what do I have? 1 plus 2 plus 3 plus ... plus 35. It's easier to see that there are 35 terms in here, maybe for some, than it was to know there's 35 terms in that series. And now I can do the formula we had. I'm going to actually use this one again. N is 35 halves. First term is 1, last term 35. And this is going to give me, again, 35 times 36. Same total, right? We could have done it that way. And yet, let's do it one other way. I want to find the sum of the first 35 terms. So it's going to be 35 halves. What am I doing now? I'm using this formula. N over 2, 2a1, n minus 1d. That's the formula I'm going to use. So it's going to be 2 times first term is 2a1, plus n is 35. 35 minus 1 times common difference is 2. Correct? I'm going to multiply by 2. Let's see how this is going to work. Again, I have 35 halves. Within bracket, I have 4 plus 35 minus 1, 34. 34 times 2 is 68. Okay, and 68 and 4 makes 72. 35 times 72 halves. 72 halves is 36. 35 times 36 is 1260. So notice, we did this 3 times. Of course, you expect the same results. But that's how you can do these. Good thing about math, it gives you options, right? So always have different ways of doing these problems. So it's not just a way of doing a task. You can do it in multiple ways. Let's take a look at another example. Let's do this one. Suppose now I want to find, let's do one where we use sigma notation. I want to find the sum from 1 to 80 of 4n minus 9. Okay, now again, this would be the sum a sub n, and goes from 1 to 80. And let's see, our a sub n is 4n minus 9. The series is arithmetic series. How do we know? Let's see. What does a n minus 1 looks like? That's when n is n minus 1. And let's do a n minus 1. This is to show that it's arithmetic. So it's 4n minus 9 plus 4 times n minus 1 minus 9. And this is going to be, let's see, 4n. Oh, sorry, I'm doing minus. Right? That's what I'm doing. Now, 4n minus, let me write this out. Distribute the negative. We get negative 4n plus 4 plus 9. Those opposites add to 0. The 9s add to 0, so you get 4. That is indeed the common difference. Now, some people actually write this out. They put n1, n2, n3, n4 like that and show that the common difference is that. You can also do it that way. So we have the common difference. The first term is a sub 1 is 4 times 1 minus 9. That's when n is 1, you put 1 in the formula here. And you get 4 minus 9 or negative 5. D was 4, and we know the 2 required information in order to do S sub 80. Notice I don't know the first, well, I know the first term. I don't know the last term, the 80th term. I could plug in 80 for n, and you can do that. But if I don't know it, then I'm going to use this formula that we used up here. We use this one. Okay, so that's the one I'm going to use. So I can say S sub 80 is going to be 80 divided by 2. And that's going to be twice first term, 2 times negative 5 plus n minus 1. Common difference is 4. And that's going to be 40 times negative 10. And 80 minus 1 is 79 times 4. That's 316. Okay, so 316 minus 10 is 306. And this is going to be 12,240. That's the sum. Now I can also do this example using previous sections method, but we really wanted to do it using arithmetic series. But call this, let's say, a check. This is my check to make sure that this is the right answer. To check it, I'm going to use a different method, the method of section 12.1. I can write this series as sigma of n1 to 80 of 4 times sum from 1 to 80 of n minus sum from 1 to 80 of 9. And using the formulas in previous section, this is going to be 80 times 81 divided by 2. And this is the formula from previous section that says sigma k is n plus 1 over 2. Okay, that formula we had. K goes from 1 to n, that one. And we also had sigma of a constant from 1 to n is n times the constant. So that's going to be 80 times 9. And we can simplify this. 4 halves, that's 2 times 80. 160 times 81 is 12,960. Minus 80 times 9, that's 720. And for the grand total of 12,240. Again, the check, I did it using method of section 1, the previous lecture. And clearly we get the same number. So isn't that cool? So many different ways to look at these problems. All right. And we are good. We just wanted to talk about arithmetic sequences and series. And please remember, the formulas we developed in this section only work for arithmetic sequences and series. Okay, only for arithmetic. They're not going to work for anything else. Okay, and with that, we are done with this lecture. Again, as always, thank you for watching and hope to have you in another video of mine. Have a nice day, have a nice night, wherever you may be. Thank you, folks. Take care.